whenever I get to present in a room like this, I like to imagine that you, the audience, are going to the cinema to watch a movie. And my favorite movies are, of course, The Lord of the Rings. I still vividly remember the first time I went to see The Fellowship of the Ring, and I became an instant lifelong fan. In fact, I have spent a large amount of time and money trying to look as much as possible as one of the main characters. I mean, you can see it, right? The resemblance is uncanny. I'm forgetting the most important part. Wait. I mean, now it's obvious, right? We could be brothers. What? No, absolutely not. I wish. I wish it was really me. But so The Lord of the Rings is not the only trilogy that I am a big fan of. This is also true for the HTTP protocol, of which the third one was just released last year. And I'm very proud to say that I played a small part in the design of the protocol. And one of the main things you need to know about H3 is that it has a lot of performance features on board, a lot of things that will help you load your web pages faster. And one of the good things about these features is you kind of get them for free, out of the box. You don't really have to do anything. In fact, if you use a hosting provider or, for example, a CDN, like Akamai, where I work, it's really as simple as flipping a switch and you get HTTP3 on your web pages. And you might think, well, Robin, there must be a catch. Maybe I have to change my web pages, to make use of all these features. And the good news is, no, you actually don't. As long as your pages are optimized for HTTP2, which they really should be by now, you should be good to go. And people who were here about 8 years ago, you will remember that this is quite different from when we moved from HTTP 1 to 2. That was a lot more work. And this, just enabling H3 has a lot of benefits. For example, Wix, which is one of the biggest do-it-yourself website building tools, they actually ran a comparison to H2. And for the largest contentful paint metric, if you don't know, that is part of Google's Core Web Vitals. Those are Google's performance metrics that it actually uses for SEO rankings in the search engine, so quite important. Google says if you have a largest contentful paint, which means the time it takes for your main element of your page to be rendered to the user, as long as that happens below 2.5 seconds, you have a fast website. And just by enabling H3, Wix got up to over 500 milliseconds improvement, even in the Netherlands, where you have quite fast networks already. So basically, you're shaving off over 1/5 of this metric just by flipping the switch on H3. I don't know about you, but that's pretty good value for money, right? So what this means is that we can, and we also do, treat the network kind of as a black box. You don't really need to know what's in there, how it works, to get most of the benefits. That's a good thing. It's also a bad thing, because sometimes, just sometimes, you do kind of, want to poke that black box just a little bit, try to tune a bit what the protocols are doing. You might use some of the features listed here on the slide that are available to front-end developers. And you often make mistakes when doing that. Because like we said, it's a black box. You don't really understand what's going on in there. And you try to use these features, but often in a suboptimal way. And so where you have these very powerful, very performant protocol features, they might quickly turn out to be a very dangerous foot gun instead. And so that's what I'm going to try to do today. I'm going to talk about some of these high-level features, why they exist, how they work, hopefully try to prevent you from making some of these mistakes yourself. Now, of course, any self-respecting trilogy can't start without a decent prologue. So let's talk about congestion control. Now, anyone who has ever had a networking 101 class will probably still have nightmares from this type of diagram, because what we're going to talk about is bandwidth. As you know, each connection has a certain amount of bits per second that it can send. This bandwidth, however, is not predefined. It depends on the medium you're using, 4G, cable, Wi-Fi, but it's also dynamic, because you're usually using a shared uplink to the internet, shared with other users and their connections. And this uplink has a maximum capacity that you want to fairly distribute across all these connections. Now, of course, users are constantly coming in and leaving the network, and so the amount of connections fluctuates. And so the amount of bandwidth for each connection also changes over time. What all of this means is that there is almost no way if you open a new connection, to know how much bandwidth it will have available. You cannot start sending at maximum speed because you don't know what the maximum speed is. The only way you can get to know that is to try and figure it out incrementally over time. And that's kind of what these so-called congestion control algorithms do. They literally start with something called slow start. The new connection will only send about 10 packets at first, about 14 kilobytes, called the initial congestion window. After that, it has to wait for a full network round trip. Why? Because the receiver is going to send back what are called acknowledgements. It's going to let the sender know, hey, I actually received those 10 packets. It's safe to send me this amount of data on the network. Then the sender can say, okay, 10 packets was safe. Let's try a bit more. Let's try 20. It sends 20 packets, again, waits a full round trip for the acknowledgements. If all those come in, okay, let's go crazy. Let's double it again, let's do 40, right? And this keeps on going until, in this example, at the 5th round trip, we get something called packet loss, which in this case basically means you don't get an acknowledgement for one or more of those packets, meaning it was dropped in the network. And that is usually a pretty good indication that you are using too much bandwidth. The network is becoming overloaded or congested. This means we need to lower our send rate again. In this example, we halve it again. And then afterwards, we can again try to iteratively find a new optimal bandwidth to use. This is a very naive, simple explanation of congestion control. Modern algorithms are much, much more complex than this, but the basic concept still stands, and that is that each network connection, even HTTP3, will go through this slow start phase. You will have a limited amount of packets available at the start, and so we need to be quite clever with how we fill them to get optimal performance. And as you'll see, this will impact everything, all the other stuff that I'm going to talk about right now. The first one being the resource loading behavior of the browsers with priorities. To understand this, I'm going to use a relatively simple web page. It's just going to have 2 resources, and then the CSS is going to have a font file that you will need later. So what happens if the browser requests this HTML page? Well, it sends the GET, and that first 14 kilobytes, first 10 packets, are of course going to be filled with the top of the HTML page. The browser receives that. It'll then request the JavaScript and the CSS that it just discovered in the head, and it's also going to send the acknowledgements back. Now it gets interesting. Now the server doubles its congestion window. It can now send 20 packets, but it has a choice to make. It has 3 different resources that it can fill those packets with. So it could say, you know, maybe I just keep on sending the HTML. Seems like a good idea. It could say, well, I've heard that CSS is kind of important for a web page load. So maybe, instead, I will fill those 20 packets with CSS. It could also say, well, maybe the user is loading one of these fancy new single-page apps that I've heard about. JavaScript might also be important. So maybe I should kind of share my packets between the JavaScript and the CSS. It could even go crazy and say, you know, I'm going to change the resource I'm sending with each packet. So many different options. I'm going to ask you a question now. Just think about it for yourself. Which of these options do you think is going to be the faster? Which is going to be the best for web performance? The top 2 or the bottom 2? Just take a second to think. So the answer here is that the top 2 are going to be the faster. Why? Well, this mostly has to do with the fact that JavaScript and CSS need to be downloaded in their entirety to actually be used on the page. This is different from HTML and some image formats who can actually be used as they are streaming in. JavaScript and CSS not so much. They can be compiled and parsed in a streaming fashion, but to actually be executed on the page, you need every last byte. And so you see, if you do the multiplexing, the round-robbining, the bottom options, you're actively delaying when these final bytes get loaded and when the resources are ready to use. That is very different from if you use a more sequential back-to-back approach on top. So let's say the server knows this and it says, okay, top one is better. I'm going to fill those 20 packets with the CSS. That's what we have here. Browser gets the CSS. Again, parses it, discovers it needs the font file, will request the font file there. The whole thing starts again, but a bit more complex this time, because now we have 40 packets to fill, and not 3, but 4 resources to choose from. And I could keep going for a long time, but I think you understand the gist of this now. And that is that how the server fills those packets can have a very big impact on web page loading performance. The problem is that the server doesn't always have enough information to make the right decisions here. Imagine, for example, the JavaScript file here. The server would not know if this is a JavaScript file in your head that is parser blocking, or if this would be a JavaScript file tagged as async or defer, and is not render blocking. Similarly, if we would have an image here, the server would not know if this image would be above default, visible to the user, or below default, and could be loaded later. The server does not have this information. The only party that has this information is, of course, the browser, because the browser is parsing the HTML and knows all about this. So basically what happens is the server is not the party that takes these decisions, it is the browser. For each request that the browser does, it is going to send along what is called a priority, an indication of importance for each resource. And the server then, much easier, it just has to listen to the browser. In this case, we had 20 packets. How do I fill the 20 packets? Very simply, the browser says, oh, the HTML is currently the most important. I'm just going to fill it with the HTML. Done. Very easy. That's the concept. That's what should happen. That's, of course, not what happens in practice. Because there are several issues here, both on the browser and the server side. Some servers, for example, simply don't listen to the browsers. I looked at this a couple of years ago as part of my research, and the top one is what the browser wants you to send, so sequentially, what we hope would happen. And you can see that even some of the most well-known open source servers kind of get it completely wrong. In this instance, Node.js kind of just ignored what the browser was telling it, defaulting to this round-robin behavior, which we've just seen is one of the most inefficient possible ways for loading a web page. And this is from a couple of years ago. I recently redid these tests. And I don't want to share results because I don't want to name and shame anyone. But it's still quite as bad as this. A lot of servers still don't get this right. HTTP 2, sadly also in HTTP 3. So there's a high chance that your current deployments have this kind of issue. Even if they don't, it's still not all good, because the browsers themselves also have some problems. First of all, the browsers amongst themselves, they don't agree on what is actually most important. And even if they would agree, they probably would not think the same as you, the front-end developer. I have a couple of examples of these. Let's see. So I looked at this a couple of months ago. Which priority do the browsers actually assign to all of these resources? The top line, quite simple. The HTML, they all agree, well, that's quite important. That's the highest priority. It seems logical. The bottom line, also logical, the CSS. For 2 of them, it's high, and then Chrome says a little bit more, it's highest priority. Everything is simple. But then we see the second line, fonts. Firefox does not care about your marketing department. Okay? Firefox does not like your custom fonts, which is almost the exact opposite from Chrome, because Chrome says custom fonts are almost as important as your main CSS. So that's kind of weird. Let's make it worse. Let's look at JavaScript. I'm going to start with just Chrome and Firefox. So they both agree that JavaScript, parser blocking JavaScript in the head is high priority. That's logical. After that, Firefox says, well, everything else is kind of the same. It's just medium priority. Chrome is a bit more fine-grained. It says, okay, if it's async or defer, it's actually low priority. Now, I can be wrong, but I think that what Chrome is doing here is what you would expect as a developer. Yeah? Because you think, in your mind, async and defer are indeed less important resources, so lower priority. Now hold on to your seats, because I'm going to show what Safari is doing. In case it's not clear. What Safari is doing here is saying all JavaScript is the same high priority. Don't care if it's in the head or in the bottom of your HTML, it's all the same. The only exception is async, which is one step lower, which I found very strange, I would have thought if one of these two would be lowered, it would be the defer, yeah, not the async. But okay, this is what Safari has chosen to do. I don't really know why. So this again, quite weird, quite big differences between the browsers. Let's again make it worse. Next example. Here we are again loading the largest contentful paint image. So like the most important image on your page needs to be loaded as soon as possible. And you probably all have heard this advice. If you want the largest contentful paint image to load faster, what you should do, you should preload it. Yeah, because preload is magic. It helps for web performance for these things. So just do that. I hope you've all heard that. Now with that context, I'm going to ask you another question. Compared to a normal image tag, so let's say the image would be in a normal image tag in the body, what do you think the preloading of the image will do? Will it actually increase the priority, make it more important? Will there be no change, or will it actually be a lower priority? Again, take a few seconds.
Which browser?
Yeah, well, no browser, just what you hope or think would happen. Because I can guarantee most of you will be wrong anyway. So let's look at this. To know what happens, you first need to know what is the default priority for an image in the body. This is either medium or low. Okay, that's probably as expected. Images are important, but not as important as JavaScript, CSS, fonts. Fine. Now again, hold on to your seats. Let's look at what happens if we preload the image. Now, am I saying that Safari is the new Internet Explorer? Yes, that is exactly what I'm saying. But that is not the point that I'm trying to make. The point I'm trying to make is this is very unintuitive, probably for you as a developer. I don't think anybody, or most of you, won't have this correct. What you probably were expecting to see is this last line here. What Chrome is doing is that the importance of the image would actually go to a much higher value, yeah? Because it's the largest contentful paint image. This doesn't actually happen. How did I force this to happen? Well, with something new called the fetchpriority attribute. Yeah? So preload, it's a bit weird. Preload really only says you need to request the image sooner. The browser needs to request it as soon as possible. It will do so still with a low priority. It will still be behind things like defer and async JavaScript. If you really want to load it before those things, you need to add a second attribute called fetchpriority to actually make this happen. So many people get this wrong. Now, you are forgiven for this because this is a relatively new feature, but it's very powerful. You don't have to use it with preload. You can also just use it on an image tag directly, for example, in the body. And you can also do the opposite. For example, if you have a carousel, where there's just one image visible at the start and the rest will be hidden until the web page is loaded, you can actually lower the priority of the non-visible images to make sure they load quite later than everything else. And there are many other use cases for this. You can manipulate priorities for JavaScript and fonts and everything else as well. I would say check that out on the web.dev link there below. For now, this is Chrome only, obviously. But the good thing is that Safari and Firefox are working on this. This is actually already in Safari Technology Preview, and also Firefox is doing this. So this is coming to a browser near you very soon. Now what all this means is that this whole resource loading thing and priorities is really quite complex. And it's also very inconsistent and unpredictable across the different browsers. And why this is a big problem, according to me, is because I think, could be wrong, but I think that you mostly test in Chrome. And if you do any kind of web performance tracking, you usually focus on those core web vitals from Google. You can only measure those in Chrome. You can't measure those in Safari. You can't measure those on iOS. Yeah? So what most of you probably do is, okay, I optimize for Chrome, and I hope, magically, these optimizations will be good in Safari as well. As we've just seen, I highly doubt that. I think that a lot of your pages are much slower than you might expect because of these differences in browsers, prioritization, and because you don't test. Now the bad thing is, I don't actually have a good solution to this problem. I can't actually tell you how to fix this, so I'm just going to ignore this for now and move on to a different topic that everybody finds much more interesting, which is, of course, the Lord of the Rings. The Lord of the Rings, they had a problem as well. They had a problem with the height of the different races. You have hobbits, you have dwarves, and then you have elves. But of course, the human actors are not necessarily the same height as the character they're playing. So they had to use all kinds of different tricks to get this to work. For example, in some scenes like this one, the taller actors had to stand on these kinds of stilts to appear larger. On other scenes, the hobbits were actually having to sit on their knees to try and appear shorter. Another technique that they often used was to use so-called body doubles, additional actors. For example, in this scene, you have the small hobbit and the tall wizard. The hobbit, this is actually the real actor. This is Billy Boyd. This, however, is not Sir Ian McKellen. This is actually a cameo by famous American basketball player Shaquille O'Neal, one of the tallest people in the world. Now, this concept of having something short alongside something large is something we also find in the HTTP protocol, of course, specifically in the connection setup and handshake. As you probably know, if you set up an HTTP connection, what you're really doing is setting up a TCP connection. You might have heard about the TCP three-way handshake that you first have to do. This takes about 1 round trip on the network. In this case, the network latency is 200 milliseconds. So it takes 400 milliseconds before you get your first HTTP data back. And this is actually not at all how we load web pages nowadays, or at least I hope we don't. What you do nowadays is add another thing in between, that is TLS, Transport Layer Security, to get our HTTPS. Now TLS also needs a kind of cryptographic handshake in the middle to do things like setting up encryption keys for the connection. So with a high latency network, you're actually waiting over half a second before you can start getting the first HTTP data in. This is one of the main reasons you would use QUIC and HTTP3, because HTTP3 doesn't use TCP anymore, it uses something new called QUIC. QUIC actually combines these two concepts, transport and cryptographic, into a single handshake, which can be done in a single round trip. So you save quite a bit of time. And it gets better because there is this magical feature in HTTP3, which is called 0RTT, where you can send the H3 request and get the response back all in the first round trip during the handshake. That is the best performance that we can ever get. The problem with this is that we can't use 0RTT all the time. There will be serious security implications behind that. What we do in practice is we use a first bootstrap connection. So the first time you go to a server, you use this kind of handshake, the long one. Once that is encrypted, you will then exchange encryption keys for the next connection after that. So this is the first, and then after that, if you do a new connection, you have those encryption keys, you can use them to encrypt this initial HTTP3 request. Okay? So HTTP 0RTT, sorry, is very powerful, but you can't use it all the time. Of course, latency and connection setup is only one side of the coin of performance. The other side is, what we already talked about, is of course bandwidth, send rate. And what we said is you start with about 10 packets, which is 14 kilobytes, thereabouts. Why? Because TCP packets have about 1.4 kilobytes of payload data available, usually. This number is quite a magic number, and has led to what I like to call a persistent myth on the internet. Because every so often, every, let's say, 6 months, somebody posts an article like this, where they say, if you can fit your entire web page or your HTML inside of 14 kilobytes, it is magically going to be much faster. You know, super web performance because you adhere to this magical number. What they're actually saying is, you know this now, basically saying if you can fit everything inside of that first round trip of that slow start logic, then you're going to be fast. That's quite obvious because you're only using one round trip. That's going to be faster than using more. So that is a good concept. The problem I really have is with this 14 kilobytes. This number no longer makes sense in the modern age. Why not? Again, this kind of only makes sense if you do unencrypted HTTP directly on top of TCP. Because TCP does the handshake, and after that, this is when this congestion control algorithm starts, after the handshake. So if you don't have anything in between, yes, you will have 14 kilobytes for your HTTP. But of course, nowadays, we have something in between. We have TLS. TLS will also have to exchange some data, things like the service certificate. These things are usually not the full 14 kilobytes, but still they use a little bit of that data. And so what you get for HTTP here is already the second round trip of that slow start algorithm. So it's usually not going to be fully double, it's not going to be 28. This here depends on how large the TLS handshake actually was, but so it's going to be a bit more than the 14. This changes again with H3. One of the reasons is that quick packets, so H3 packets, are actually a bit smaller at the start of the connection. They only carry 1.2 kilobytes of payload. They grow larger over time, but at the start, they're only 1.2. So you kind of get an in-between here. It's not quite this, it's not quite this, it's somewhat in between because the packets are smaller. And then finally, zero RTT is even weirder. Zero RTT has all kinds of security issues. And to prevent something called an amplification attack, you don't need to know the details, to prevent that, most zero RTT setups will actually only allow you to send about 4 kilobytes in that first round trip, which is a lot less than that 14 kilobytes. So these are already very different. Let's make it worse. Where does those 10 packets come from? That's actually what you get if you have a default Linux server setup. That's the default in the Linux kernel. Has been for years. But if you use, for example, a CDN or a big hosting company, they often tweak these values in their own custom kernel setups to give you a lot more data at the start of the connection. Yeah? So what all of this means is, I think it's very unlikely that you will fit your entire web page inside of that first round trip. Whether it's 14 or 50 kilobytes, only very trivial websites will completely fit into that. But the concept of keeping those critical resources, those things you really need to load to render the first part of the page, inside of as few round trips as possible, that is of course still very, very valid. This means things like minification, tree shaking, and especially compression, things like broadly compression, are super important for all the resources, but especially those at the start of the connection. So your HTML, your critical CSS, your first JavaScript bundle, those should be as small as possible to maximize your chances of fitting inside of those first few slow start round trips. Right. Now I can see a couple of people drifting off. I know it's boring, nobody wants to listen to this. So let's talk about something a bit more interesting, which is of course, women with beards. Now in Lord of the Rings, there's a scene where the dwarf Gimli, he says, "It's true you don't see many dwarf women." And one of the other characters replies, "Well, it's because of the beards," indicating that dwarf women have quite masculine features. And there is an extended scene in the extended version of the last movie. They're having a party and the dwarf is drunk, and he says this. He says, "It's the dwarves that go swimming with little hairy women." Now, if you don't think that that is one of the greatest lines ever written for any movie, I don't think we can be friends. This is just amazing, okay? Now, this whole concept of masculine women is actually part of the main story as well, mainly in the character of the princess Éowyn, who desperately wants to go to war to help defend her country, but she can't because she's a woman. So what she does is she dresses up like a male soldier so she can ride into battle. And it actually has a very good turnout because she ends up killing one of the main antagonists of the story. Talk about girl power. My favorite part of all of this is, however, that if you ever see one of the coolest scenes in all of the movies, with all the horses at the end, you know, the Riders of Rohan, again, according to the story, these are all male soldiers. In practice, the actors that you see are almost all women with beards, with fake beards and fake mustaches. Because they were filming this and they needed to find actors who preferably had their own horses in New Zealand where they were filming. And there weren't that many men around. So they also invited all the local women who came en masse with all of their horses. And so most of the Riders of Rohan are actually women with beards, which I find just an amazing anecdote for these movies. Now, this concept of replacing something inferior, the men, with something clearly superior, is something we also see in the HTTP protocol with a feature called server push. Now, up until now, I've been pretending that if the browser requests an HTML file, the server is immediately going to send back some of that file. In practice, you all know that that is not very likely to happen. Usually, there is going to be a little bit of time at the server, for example, render the page, if you have to do something like a database call. And so during this time, the network is actually going to be idle. It could be sending data, but it's not, because it's waiting for the page to render. This idle time is sometimes called the server think time. The server think time is a bit more complex if you use a setup with a CDN, so with edge servers, content delivery networks. What happens there is you basically rent servers from a company like Akamai or Cloudflare or Fastly. We have thousands of servers distributed across the world. So your end user, your browser, doesn't connect directly to your origin. It connects to one of our edge servers. That edge server is then going to connect to the origin, where you do the rendering and the database calls, and then you come back. So basically what you have in a CDN edge setup is not just that server think time at the origin, you also have this round trip between the edge server and the origin. And this means that the network between the browser and the edge here is actually idle for quite a long time. You have a lot of window of opportunity where you could be doing something with the network here, but you're stuck waiting. And this was the idea behind server push. The idea was, okay, if we're waiting, why not use the network time to send something useful to the browser? We are going to start pushing payload data for resources we know the browser will need. The critical CSS, the JavaScript, whatever have you. So that by the time the index.html comes back from the origin, you have two benefits. One, you already have all these resources. You don't have to wait for them. And two, as you can see, the congestion window has grown. It started at 14 kilobytes. By the time we have the HTML here, it's already over 100 kilobytes. And the HTML can be sent in one round trip. Yeah? So this should improve page loading performance by quite a bit. Conceptually, that's what we want to happen. It's not what actually happened. Because push had a lot of problems. One of the main ones was that it was very difficult to know which data the browser had already cached. So you would often end up pushing CSS and JavaScript that was already there, so you were kind of sending useless data. Another problem is that you can only push resources on the same origin server or the same domain as your HTML, which is kind of inflexible. And lastly, of course, most of the browsers had a lot of inconsistencies and even bugs in how they implemented this. Yeah? So push, consequently, was deprecated in Chrome. So they had this, they have now disabled this, you can't use it anymore. And officially it's still part of the HTTP3 standard, but nobody has ever implemented it. So this was kind of dead on arrival in the standard. This has always made me a bit sad because, like I said, the concept of using the server think time is actually quite powerful. It was just a push mechanism that failed to perform. And so that is why we are now trying to replace this with something new, a new mechanism, which is called 103 early hints. And it's very similar to push, but instead of actually sending the payload data, we are first going to send a list of links of resources that we think the browser might need. What does that look like? It's again something you probably all know. These are just preload and preconnect statements. Normally you would put these in the HTML. Of course, we don't have any HTML yet. That's what we're waiting for to come from the origin. So what 103 early hints actually does is puts these in the HTTP response headers of the HTTP level data. So slightly different syntax, but the concept there is exactly the same. So what happens? The browser gets the early hints, and it can then itself determine which of these to request. For example, if they're already in the cache, it just skips the resources, of course. It can also apply correct prioritization to these resources, which also was not possible with push. So this is already a lot better, But it's even better than that, because I think the killer feature of 103 early hints is that you can also use this to preload stuff on different domains. This means that while all of this is happening, while you're waiting for the HTML and loading all of this, in parallel, next to this, you can actually, for example, start a new connection to, let's say, your static subdomain, where you might be hosting your fonts. And so your font can be loaded fully in parallel with everything else. This was impossible with push, and now trivially supported in 103 early hints. And I think this is the thing that will make early hints very, very powerful in practice. So we have started implementing this at Akamai, at the CDN Edge. So this is an example of where we don't use it yet. So you see you have to wait for the HTML to come in. So this dark blue here, this means that we actually get the HTML data. It's quite late because this is a search page, and so it had to do some database lookups. And so these sub-resources are actually quite late as well. If we enable 103 early hints for the first 4 there, first 5, you see a dramatic improvement. Yeah? We don't have to wait for the HTML, no. We get these as soon as the CDN Edge can send them back, so very, very early on. And what you see is these are fully downloaded, even the third-party resource, even the one that needs a separate connection to be set up, fully downloaded before we get the first byte of HTML back. A secondary benefit here is that also these images, which were actually delayed by the browser here, because the browser wanted to get these things first, these images are now immediately requested after the HTML, because everything else was already in. So you again get like a double performance benefit sorry, for using this feature. And it gets better. Final thing, I'm going to make the circle around again. I talked to you before about this zero RTT thing. So very fast, fast as we can go, but the downside is that a lot of times you will only have about 4 kilobytes available, which is not enough to fit anything useful, at least in terms of payload data. But of course 4 kilobytes is more than large enough to fit a bunch of preload or pre-connect hints. Yeah? So combining these two things in practice, you will actually be able to do even one round trip better than what we already have. Now, nobody has actually put this into production yet, I think, but it's interesting to see where this will go in, let's say, the coming year for maximum performance. With that, I am ready to have a bit of a conclusion, of course, as any good talk. I think it's quite clear that all of this is hopefully a bit interesting, but also quite complex. And that these features are not something you just can use willy-nilly. It's very easy to get things wrong. For example, a lot of people are misusing the preload feature quite a bit. That's what you see most in practice. And I hope it's now a bit clearer why you should be careful with this in the future. It also sadly means that I don't have very specific recommendations to make, because it really depends on your specific web page, the browser that you want to optimize for, and the server-side deployment you use. CDN versus no makes a big difference. What I do want to say is that all of this network-related optimization stuff is really not something you should focus on at the start. You know? I know some of you like to take pictures for Twitter or something like that, so I wanted to throw you a bone here. Most web pages we see in the wild have a lot more low-hanging fruit, a lot more things that are much easier to optimize and give a lot more gains than what I've just talked about, right? So these protocol stuffs and the optimizations are things you look at after you've optimized most of the other things. Yeah, especially things like images or the JavaScript you are loading. But once you've done that, you can really squeeze quite a bit out of these apps we've seen as well. The final thing I want to impart is I hope it's very clear to you now how important it is to have a good configuration for your network protocol. And this can be quite complex to do yourself, right? If you have to do this congestion control logic yourself, you have to make sure you do this prioritization with a good server. And then you need to host yourself a server that does HTTP3 and 0 RTT. Let me tell you, very difficult to do yourself. This is why I would recommend to use a CDN. And believe me, I would be saying this even if I wouldn't work for a CDN, right? CDN is one of the easiest things you can do to get better web performance in a worldwide setting. right? So with that, I would say thank you all for listening. I wish you good luck in trying to apply some of this.